Okay, so just now is the easiest case. Okay, so the LC oscillator without any energy loss. So it's like even high school student will be able to understand. So here we have introduced some energy loss here. Okay, we introduce internal resistance. Okay, so here is called a damped oscillation. Okay, damped oscillation in an RLC circuit. So not RC anymore. We have not LC anymore. It is RLC circuits. So to analysis, okay, to analyze the oscillation of the circuit, we write an equation for the total mechanical energy. Okay, so this is still the same as the previous case. Okay, so we still have U equals UB to be this form. Okay, however, the total energy decrease. Okay, so we have some energy decrease. Okay, because we have a resistor. The resistor will consume energy as there are some voltage and current going across it. So the rate, okay, so here it says the rate of the transfer is du dt is negative I square out, okay? So originally the power consumption of the resistor is I square out, but here is considering the du dt, the rate of change of the total energy. So which means it should be a negative. If it is positive, it turns out to be generating some energy, okay, injecting more energy in the system. So this is not the case. Okay, so the resistor is actually consuming the energy in the system. So this should be a negative value. So we have a du dt equals negative I square out. So which means that, yeah, on the left side we still take the derivative of the u with respect to time. So it turns out to be Li and then di dt. Okay, just as before. And then for the next term, we have a Q over C and then dQ dt equals negative I square out. Okay, so here we also make use of Q equals, dQ dt equals I. Yeah, and then di dt equals d2q dt2, something like this. Okay, so that we can actually, okay, turn this one into I, so that we can cancel the I on both sides. So this I, and also this I can be cancelled. And also we can change di dt into d2q dt2, okay? So the first term will be L d2q dt2, and then plus the second term, only q over c remains. And then why not moving this to the left side? And then actually we can also try to change I to be dq dt. So we have R dq dt to be 0. And then actually we can also put this term in between. Okay, so this is the first derivative, this is second derivative, this is the original function. And then we actually divide L on both sides, so that it turns out to be the second derivative plus this one R over L goes to the first order coefficient dq dt plus 1 over LC. Okay, here 1 over LC and then times Q, okay, equals 0. So this is a full second order constant coefficient linear ODE. So actually, if we try to change this one into S squared plus R over LS plus 1 over LC equals 0, of course, we can have three cases. We can have the b squared over minus 4ac to be larger than 0, equal to 0, or smaller than 0. But we don't really care about the first two cases. Okay, for the first two cases, if you still remember, okay, if it is larger than 0, it turns out to be two exponential function with a negative exponent. So it will just tend to 0 when t becomes large. So this is not oscillating, okay? And even for the second case, okay, if b squared minus 4ac is 0, so in that case, it will be like a linear function, a plus bt times the exponential function with a negative exponent. It still decays, okay, with respect to time. So it won't oscillate either. Okay, so what we need to have is b squared minus 4ac, okay? So here we have a b squared is r squared over l squared minus 4ac, 4 over lc to be less than 0. So this is the condition, okay? This is the condition for the for this RLC circuit to be able to oscillate. Okay, so this is not that difficult because if you pick R, okay, so if the R is small enough, then it will be okay. If R is small enough, then it will be okay. So in that case, it just tells you that. So actually, the textbook don't teach you how to solve the ODE. It just tells you that for this differential equation, the solution is like this. Okay, it's like this. And then here, omega prime is this one. And then where omega is still 1 over square root of LC. Actually, okay, so this is the energy method. We can also use the potential method to derive the similar things. Okay, so let's do it. So suppose this is VC, this is VR, this is VL, okay, something like this. And then we have I is clockwise. So using the KVL, we have a VL plus VR plus VC will be 0. Yeah, because this is like voltage drop, dropping 3 times, going back to the original point. So VL plus VR plus VC should be 0. Okay, so VL. Yeah, so VL. Let me see. Okay, so here we will have I equals C dVC dt. And then also we have a VL equals L di dt. Okay, so these two formulas are for the inductor, capacitor and inductor. So that VL will be L di dt plus VR is a resistor, so it will be nothing but R times I. And then VC is so VC will be 0. Okay, so here we try to take the derivative on both sides. Take the derivative on both sides. Okay, on the right side, of course 0. So the derivative of 0 is 0, and then multiply by C. So it turns out to be LC, and then D2I dt2, and then plus RC, and then di dt, and then plus C. So let me see. Yeah. So C dVC dt. Okay, C dVC dt equals 0. Okay, so C dVC dt will be I. Okay, so it turns out to be LC d2I dt2 plus RC di dt plus I equals 0. So we just try to divide LC on both sides. We have d2I dt2 plus RC over LC will be R over L, and then di dt plus 1 over LCI equals 0. So this is this is the formula, okay? This is the formula that we get here, okay? So actually, this is an equation for the Q, okay? But the first order coefficient is R over L, and then 1 over LC here. So R over L here, 1 over LC here. But this is also for I, okay? So you can just prove it by taking the derivative and then replace dq dt by I. Okay, you get it. So so here we have this one. Okay, we have this one. So so here we actually can make it like s squared plus r over ls plus 1 over lc equals 0. So this is the auxiliary equation or the characteristic equation. So let me put it here, s squared plus r over ls plus 1 over lc equals 0. So so we need to have delta equals b squared minus 4ac to be less than 0, which is r squared over l squared minus 4 over lc to be less than 0. So we need to guarantee, okay, this condition is met. So here s will be negative b, okay, negative b, a is 1, so negative b over 2, so r over 2l plus or minus j. Okay, so b squared minus 4ac is less than 0. So in the square root will be 4ac minus b squared, which is the negative of this one, and turns out to be something like, yeah, so actually will be 4ac minus b squared, and then all over 2. Okay, so we can just put 4 in the square root. So it turns out to be 1 over LC minus r over 2l and then whole square. Okay, so this is nothing but minus b plus or minus square root of b squared minus 4ac all over 2a. So you can just yeah, if I make it too fast, you can try to verify it by yourself. Okay, so here, based on this imaginary part, we know that omega prime is actually square root of 1 over LC minus R over 2L quantity square, which is actually this one, Here, okay, just put omega to be 1 over square root of LC. Okay, so so if we try to define, okay, omega prime to be like this, so we can actually have a negative R over 2L plus or minus J omega prime, and then in that case, okay, so this is the root, so the complementary solution can be written as exponential to negative alpha t, okay, RT over 2L, and then cosine, okay, originally just tell you that it will be A cosine of omega prime t plus B sine of omega prime t, okay, A and B are undetermined variable. But actually, according to high school trigonometry, you can always combine the cosine and sine with the same frequency. And it turns out to be exponential to RT over 2L. And then this one turns out to be a big I, and then cosine of omega prime t plus phi, okay. Omega prime t plus phi. Okay, you can always convert it like that. Using some compound angle formula. Okay, using some compound angle formula. Yeah, so this is the damped oscillation. The damped oscillation means if you disregard this term, okay, so it will be like I times cosine of something, okay, cosine of something. But with the R, this thing, okay, this thing will be like exponentially decay, yeah, because this is not T, this is L. This is L, okay, this is L, okay. So R, T2, okay, this whole thing is positive, so this is a negative exponent, okay, which means that this thing is decaying, decaying, okay. So it will be like originally without the exponential, it will be like something like this, okay, sinusoidal, okay, a sinusoidal wave. But here it turns out to be like this, okay, so we have a exponentially decay envelope, and then it turns out to be something like this, okay, so this is actually the exponential to negative RT over 2L. This will be the negative exponential, or maybe including the I. Okay, negative I exponential to negative RT over 2L. Okay, so this plus or minus will be the boundary between the curve. I mean the curve between these two boundaries. I mean, yeah. So yeah, so this is pretty much like this. So for the RLC circuit, and then it turns out to be like this, to be like this expression. Although this is Q and capital Q, and then but for the later part will be exactly the same. Also, this part will be the same. Okay, one thing you need to pay attention is that if it is only an LC oscillator, okay, so the natural frequency or the oscillation frequency will be nothing but this 1 over square root of LC. Yeah, but here we have this resistor. Okay, so it's like, okay, making the oscillation slower, so that this one, okay, if we don't have this term, okay, it will be like omega squared. Taking the square root will be omega itself. So this is turns out to be this frequency, but this term is positive, so it will be like omega squared minus minus something positive. So which means that this difference will be smaller than omega squared. Okay, so it will be always smaller than omega. Less than omega. Yeah, because we have some resistance. Okay, so that it try to avoid that the LC oscillator to oscillate as fast as the original, as the LC oscillator. Okay, so the frequency becomes smaller. Yeah. Yeah. So an analogy to the spring mass system is like here. If we still have this spring with a coefficient k, and then we have a mass here m, and then here, okay, rather than the force, okay, from the spring, we also assume that there will be some frictional force to be negative b dx dt. So which means that we try to model the frictional force to be with an amplitude proportional to the velocity. Okay, so if it doesn't move, there won't be any frictional force. If we try to move, okay, there will be frictional force proportional to the velocity, but in opposite side. So we have a negative side here. Okay, so we don't try to make it too complicated, yeah, because if you learn the frictional force in the mechanics, it would be much more complicated. Actually, a quite non-linear situation. So, but I don't try to make it that difficult here. Try to maintain it to be a linear system. So that in that case, we have f equals negative kx and then minus b dx dt. Okay, so this is the force. Okay, so the Hooke's law. Okay, the force comes from the spring. and then this is the frictional force, the total force acting on this mass, and then equals m d2x dt2. Okay, so the Newton's second law of motion, so that we can actually move all the terms to one side and then divide m for the whole equation. So that we have a d2x dt2 plus b over m dx dt plus k over mx equals 0. So that, okay, so that so that comparing this one with let's say this one, okay, with let's say this one, LC, okay, or maybe this one, I try to put it behind, okay, maybe okay, d2 v dt2 plus r over l dv dt plus 1 over lcv equals 0. Okay, so comparing these two, so it will be like you turn R to be a B, okay, so resistor, okay, to be like a coefficient for the frictional force. It somehow makes sense, okay. L turns to be the M, okay, so the inductor turns to be the mass, and then also 1 over LC turns to K over M, okay, so the natural frequency of the LC oscillator and the LC and the natural frequency of the simple harmonic of the spring mass system. Okay, so after making this change, okay, you can change this to that, okay. So and then all the equation we derive there, okay, will be okay. So this is the analogy, okay, this is the energy. If you have interest, you can also try to solve this, okay. So actually it will be the same as solving this one, okay. So there will be 3 cases, but what we concern is that delta is less than 0, which makes the system oscillate, okay. So there will be a corresponding condition to satisfy, which means that the frictional force can't be too large, okay, otherwise it won't oscillate. Okay, so here we have a sample problem. So a series of RLC circuit has inductance, okay, capacitance like this, resistance like this, and then and begins to oscillate at time t equals 0. So what is the time? At what time t will the amplitude of the charge oscillations in the circuit be 50% of the initial value? Note that we do not know that initial value, okay, we don't need to know, yeah, because what we really concern is the exponential to negative r over 2 lt to be t0 to be 0.5, yeah, because what it really asks is that, yeah, so actually I is something like this, okay. So originally when t equals 0, which means that this exponential term will be 1, okay, and then so the initial current or the initial charge will be like this is 1, okay, this is 1. So it just asks, what will be the time so that the amplitude of the charge turns to be 50%. So which means that this exponential term to be 0.5 will be the time we would like to find. Yeah. So actually, R over 2L T0 will be natural log of 2. Okay, so taking the reciprocal on both sides and then take the natural log on both sides. So T0 will be 2L over R natural log of 2. And then we can plug in all the numbers. 2 times 12 times 10 to negative third power over resistance is 1.5, okay, 1.5, and then natural log of 2. So this is 11 millisecond, okay. So yeah, so this is related to the resistance in the inductance. Okay, so for the next question, how many oscillations are complete within this time? Okay, so here we need to compute the omega prime, which is square root of omega squared minus r over 2l whole square, which will be square root of 1 over lc minus r squared over 2l squared, something like this, and then we can plug in all the numbers. So this is 1 over 12 times 10 to the negative third power, and then we have 1.6 times 10 to the negative 6. Okay, so this is 1 over LC, and then we have 1.5 square, and then over 2 times 12 times 10 to the negative 3. Okay, 3 square, and then taking the square root of the whole thing. Taking the square root of the whole thing. So this is the natural frequency. Okay, so this is the not the natural. This is the oscillation frequency for this RLC circuit. So it turns out to be 7.217. Okay, so the SI unit will be radian per second. Radian per second. So this is angular. This is angular frequency. Angular frequency. The angular frequency and the linear frequency will have a 2 pi factor in between. Okay, we have a 2 pi factor in between. So omega equals 2 pi L, something like that. So if you would like to turn it into linear frequency, you need to divide the value by 2 pi, and then it will be hertz. Okay, in for the SI unit. Okay, so for the number of oscillation is that here is 11 milliseconds. So we have 11 times 10 to the negative third, and then 7.217 times 10 to the negative third over 2 pi. Okay, so because this is the time, this is the angular frequency, and then divided by 2 pi will be the linear frequency. So frequency multiplied by the time will have no unit. Okay, number of oscillation, how many times does not have any SI units. Okay, so it turns out to be 12.6. Okay, 12.6. And you can actually consider like 2 pi over this 7.217 times 10 to the negative third will be the reciprocal of the linear frequency, which will be the period. Okay, so F times T will be 1. Okay, F times T will be 1. So this is the period. Okay. So this value divided by 2 pi will be linear frequency. So you can consider it putting this one underneath. Okay, so it will be the period. Okay, the period in the denominator. So the total time divided by the period will be the number of period. Okay, number of period, which is the number of oscillation, which is 12.6. Okay. Or similarly, omega t will be 2 pi. Okay, so this is something you can take reference on. Yeah, okay, so here, okay, so after finish the simple part, okay, so this part will be, to me, it is quite strange. Okay, it is quite strange. At least for the textbook, I will say the textbook is incorrect. Okay, the textbook is at least for the previous version. Okay, I I just looked at the older version. I'm not sure whether the 8th or 9th edition. So far, it's already more than 10, I think. So I'm not sure whether it makes it more correct. I'm afraid not. I'm afraid not. Yeah, because yeah, I think it would be the physics guy considered to be correct. Okay, but I don't think. Okay, I don't think those are correct. So the phasors must be complex number. Okay, the phasor must be complex number. But in the textbook, it tries to make all the things real value. So I don't think it makes much sense. Okay, so here let's come to the force oscillation of the free simple circuit. So starting from here, we try to provide AC source. Okay, AC source for the RLC circuit. Okay, so which means the input will be sinusoidal. The input will be sinusoidal. So if you try to find the voltage or current over the time very precisely, of course you need to write out the ODE as before, and then you try to solve the ODE, and then here we have the sinusoidal as the input. So you can explain, you can expect for the VP, you also assume the particular solution to be also sinusoidal, and then plug in it, okay, to solve the whole thing out. So it will be quite tedious. So here the idea is we don't care about the homogeneous equation part. Okay, yeah, because as a stable system, okay, the homogeneous solution always tends to 0 when t is large enough. So here we will consider the steady state. Okay, we'll consider the steady state. Okay, in Chinese called 稳态. Okay, steady state. 稳态. Okay, so we don't care about what is happening in between. We just care about, okay, finally, what it will be. So I would say, okay, for any linear system, not only RLC circuit, but also for other linear system, if you have a sinusoidal input, the output, okay, the output in any form will still be a sinusoidal with the same frequency, yeah. But the amplitude and the phase may be different. Okay, so this is the characteristic of a linear system. So here, okay, here we try to introduce something called a phasor, so that we can use a complex number to represent a sinusoidal function, so that we don't need to solve the ODE. Okay, we just need to do some algebraic computation, but in the complex domain. In the complex domain, we need to deal with the complex number. Okay, multiplication, division, something like that. Or of course, addition and subtraction. So in that case, yeah, computing complex number is easier than solving ODE. Okay, so yeah, but we need to sacrifice, or we don't know the homogeneous solution. Of course, you will ask, why the math is correct. Actually, it is coming from, yeah, actually, the Fourier transform actually will tell you why it is correct. Okay, so if you have a ODE describing the linear system, then you take the Fourier transform. Okay, you will find, okay, what you find here. But of course, Fourier transform is out of the scope here, too far away. Of course, I know, but yeah, this is too far away from this course, so I don't try to talk about what is Fourier transform here. Yeah, the simple equation is that to take a Fourier transform xj omega t of a time domain function xt will be like exponential to negative j omega t dt, and then integrate from negative infinity to infinity. So this is the Fourier transform. Of course, we have a Fourier series for periodic signal, but yeah, so this is a general case for the non-periodic signal. Okay, so we can always use the Fourier transform to take a look at its frequency domain. Yeah, of course, as an engineering student, I think you will learn it later. Okay, but I will not talk too much about the Fourier transform here. Okay, so anyway, coming back to here is that okay, so if we have a resistor, which will be the easiest case, okay, which will be the easiest case. Here, okay, we only have a resistor connecting to this AC EMF, okay, the alternating EMF, alternating current EMF, okay, E to be EM cosine omega dt. Okay, so VR, okay, because it is just a series, okay, with a single resistor there, so VR will be EM cosine omega dt. So here we introduce the phasor to be like VR to be IR times R, okay. So it will be like, yeah, so actually the idea here is the impedance, okay, the impedance, okay. Originally, resistance in Chinese is called 电阻, okay. So so impedance in Chinese is called 阻抗, okay, 阻抗. So of course, impedance in general case is a complex number. C in general will be R plus JX, something like this. 电阻, okay, referring to the real part, okay, so takes the first word in the impedance in Chinese. Actually, the X, okay, in Chinese is called 电抗, okay. I somehow forgot the English name. Yeah, so actually, R plus JX is the general impedance in the complex domain, which is called impedance. Chinese called 阻抗. So the complex generalization of resistance of a resistor is ZR also for resistor only. So its impedance is still ZR to be R. I don't try to go through here because you will feel like it is quite redundant. Yeah, but the idea here is like so far what you can really observe is like a VR will be like the amplitude of the voltage, and then IR will be the amplitude of the current. But it is not that yet. But for the resistor case, you cannot observe too much here. So let's go to the other case, which is the capacitor. So here, similarly, we have an AC EMF here connected to a capacitor. So here we have VC, we have IC here. So here we have E equals EM cosine omega dt as before. So VC will be capital VC. Okay, so this thing is the phasor of VC. Okay, phasor of VC. So turns out to be VC cosine of omega dt. And so far this phasor is still the amplitude of the voltage. Yeah, but for the current, it is not the case. So for the current, IC equals CdV CdT. So we plug in this one here. So to take the derivative of the cosine will be negative sign. So we have a negative sine of omega dt. And then for the chain rule, the omega d will comes out. Okay, so we have this one due to the chain rule. And then C and VC are the original factor. Okay, so we just leave it there. And then we need to make some transfer. Okay, so we would like to convert this sine back to a cosine. Okay, so the idea here is sine of omega dt. Okay, with a negative sign, or negative sine of omega dt is actually cosine of omega dt plus pi over 2. Okay, so this is some formula in the high school trigonometry. So you need to slightly memorize it. Okay, the simple idea is for the second quadrant, of the sign is positive, with the negative sign will be negative. So the second quadrant of the cosine will be negative. So the polarity match, okay? Yeah, because if you still remember, if you plus or subtract pi over 2, sine returns to cosine, cosine returns to sine. So this is the idea. So I hope you still remember the formula for the trigonometry angle transform. So we have this negative sine becomes cosine of something plus pi over 2. Okay, so here the idea is we try to consider the IC, okay, the phasor of current, the phasor of current. Of course, the IC takes this whole expression. So the phasor of IC will be like, okay, so first is this one. This is the amplitude of IC. So so it will be omega d CVC. But we need to add something else, okay? Try to put it a little bit lower, okay? Omega d IC, okay, omega d CVC here, okay? So it is the amplitude, but also with this exponential to j, but with this angle, okay, pi over 2. Okay, what is exponential to j pi over 2? Okay, so hopefully you still remember the Euler's formula. Okay, Euler's formula. Exponential to j theta will be cosine of theta plus j sine theta. So cosine of 90 degree is 0. Okay, so the real part is 0. And sine of pi over 2 will be 1. Okay, so this is nothing but j omega d CVC. Okay, so this turns out to be a complex number, or at least a pure imaginary number. Okay, so I would say the phasor of IC should be this complex number. Okay, but in the textbook, I'm afraid I just make it a real number. So I don't think it's correct. So in that case, we try. Okay, we will make it like, okay, so here we have a IC, we also have this VC. So we try to make it like a VC over IC will be 1 over j omega d C, okay? But here, okay, we would like to make the variable easier to recognize. So we replace omega d by omega. So it turns out to be the impedance of a capacitor will be 1 over j omega c. Okay. Of course, if you like, you can make it like what negative j. Okay, negative j over omega c. But yeah, as a circuit guy, I never do this. I always use 1 over j omega c as the impedance of a capacitor. So yeah, so this is the impedance of a capacitor. And as much as if we introduce the impedance and also the phasor for the capacitor and also for inductor in the next page, we will have the phasor of VC and also the impedance will satisfy VC equals IC times ZC. Okay, so this is a general form of the V equals IR. Okay, V equals IR is the Ohm's law. It's only the resistor relies on this law. But if we introduce the phasor and also the complex impedance here, so all the RLC and its phasor, okay, this phasor and also the impedance will also satisfy this general form of Ohm's law, which is like V equals I times Z. Okay, Z is the impedance. So this is what we want. The only cost is we need to deal with the complex number. But yeah, of course it is more complicated than calculating the real number. But at least calculating complex number is much easier than calculating the ODE. Okay. Okay, so this is the case for the capacitor. So the next case for the inductor will be similar. So we have the same assumption, and then we have IL to be like this, and then VL equals L di dt. So we plug in it here. So at here we also have this expression, and then similarly we try to change this to the cosine. Okay, actually the same thing. The only difference is left side is VL, right side is this stuff. Okay, this side is IC, this side is the other stuff. Okay, so finally we can have this. Okay, we can have this. Taking the VL, the phasor of the VL will be omega D, and then IL. This is the phasor of I, and then exponential to also this J pi over 2, which is J omega D L IL. Okay, so VL over IL will be J omega D L. Okay, so in that case, this is the impedance of the inductor. Turns out to be J omega DL. CL will be J omega DL. So, so RLC are the simplest case for the phasor. So R will be real. Inductor will be positive imaginary. Okay, and then the capacitor will be negative imaginary. So that somehow the inductor and capacitor can cancel each other. Okay, in this sense. So as much as similarly, as much as we introduce the phasor and the general impedance, the complex impedance, it will also satisfy this general form of Ohm's law in the complex domain. So VL equals IL times CL. Okay, VL, IL here are the phasor. These are the phasors. Yeah, the phasors. Okay, so maybe